Okay, can you please confirm that you can see the presentation? Hello?
Yes, sir, it is visible.
Okay, thank you. So I'll just briefly finish the last pending topic from uh, spherical polar coordinates. So in the last class, this was the point where we ended, where you have to find the total area of the open outer face. And I told you very, uh, pointedly, categorically that the rule of the theta integral is that the limits must go from 0 to pi, whereas for the phi integral, it will go from 0 to 2 pi, unless otherwise mentioned. So that these are the default limits. So if you don't do that, then there will be mistakes in your calculation. So, I mean, I gave some reasons for that, some algebraic, some geometric. Anyway, so the last topic to take up is this. So as I said, the open outer phase has the area element r squared sine theta d phi r cap as it goes out this way. But volume element is a scalar quantity, but the volume element must have three d's, d theta, d phi, dr, as you have, or in Cartesian coordinates, let us say you have dx, dy, dz, whereas a surface element has two d's, d theta, d phi. So how to calculate the total volume if you're given the volume element? Well, you say, suppose you've been given a sphere of radius capital R. So then you'll have to integrate the R integral, R squared dr, from 0 to R, capital R that is. Sine theta d theta, as I said, unless otherwise mentioned, the limits are 0 to pi. And for phi, the limits are 0 to 2 pi. So now let us compute sine theta d theta. When you integrate it, as has been shown over here, the integral will be sine theta d theta. The integral sine theta, the integral of that is minus cos theta. Going from 0 to pi, it'll give you, I mean, there's the minus sign already outside. This will give you -1 and -1. So -2 with the minus sign already outside, that will be 2. So remember, the theta integral always gives you 2 between the limits 0 to pi. And so that is what you have. And the phi integral will give you 2 pi. So the theta integral gives you 2, the phi integral gives you 2 pi, and the radius integrated from 0 to capital R will give you r cubed by 3, 0 to r, and then you put the value of that and you'll get 4/3 pi r cubed. This is the volume of a sphere. I believe you're familiar with this formula. It comes from the spherical polar coordinate system in the way we have just discussed. Okay. Now, before I end, I'll just touch upon a little bit. Now, why have we talked about all these curvilinear coordinates, cylindrical coordinates in the S5Z system, or the spherical polar coordinates in the R theta phi system? Here's a brief discussion on that. Suppose you have a line of charges, or you have a current flowing. The current path is indicated by this arrow. For the case of a line of charges, the field lines are going to radiate outwards from the axis. This axis contains charges. And these field lines are going to be symmetric about this axis. What do I mean by symmetric about this axis? If you go the same distance from the axis in any direction, then any direction confined to a disk plane. It's not above this disk or not below this disk. If you go to any direction, go towards any direction by the same distance, then the field strength will be the same. You could be anywhere on this circle and you will experience the same field strength. Right. Similarly, when you have a point-like object, then a point-like charge, let us say, it's, let's say, a negative charge or gravity, a particle. Then from any direction you approach the charge, if there is the same distance to be covered, then you will feel the same force everywhere on the surface of a sphere. That's why you call it spherical symmetry. Here you call it cylindrical symmetry because from the axis, if you go the same distance confined to a plane, and then you can be on any of the planes stacked one above the other, this whole structure is the surface of symmetry of this whole structure is a cylinder. So examples, magnetic field lines about a current. See, in the case of the magnetic field, the field lines will go round and round. Whereas in the case of the electric field, the field lines will radiate outwards on the plane. However, there is still a circular symmetry. In this case, there is also a circular symmetry. You can be anywhere on this circle and you will still feel the same magnetic field. So magnetic field lines around a current, electric field about a line of charges. So when you have uh, this kind of a physical system, it will be best for you to work with the cylindrical set of coordinates. Why? First, let me just read out a few things. Magnetic field lines about a current, as in this diagram, or electric field lines about a line of charges. Here, field depends only on S in the S phi Z coordinates. In the S phi Z coordinates, the field will depend only on the S vector, S coordinate, not on phi, not on Z. So that's why you'll be working with a single coordinate. That is the advantage. That is the mathematical advantage of taking cylindrical coordinates. And so all vector differential operators will only have the S variation. Suppose you work with the vector differential operator del in the XYZ system. You'll have to work with del del X, del del Y, del del Z. 3 variation you have to worry about. But you judiciously choose a kind of coordinate system where there is only variation with respect to one coordinate, then you just have to, instead of using partial derivatives, you just have to work with a full derivative. That will make your mathematical task so much easier. Okay, now let us come to the next point, spherical symmetry about a point. As I've written over here, electric field lines due to a point charge or the gravitational field. Here the point charge is electric field lines due to a negative charge or gravity. So it's an attractive field. Once again, I tell you, field depends only on the coordinate r in the r theta phi coordinate. For instance, anywhere on the surface of the Earth, if you approximate the Earth to be a sphere, which is not a bad approximation. So if you approximate the Earth to be a sphere, anywhere on the surface of the Earth, you will feel the same gravitational field strength. It will not vary from one latitude or one longitude to another. What matters is how far you are from the center of the Earth. That is to say, the radial coordinate. Okay. So once again, I have just mentioned all vector differential operators will only have the r variation, the radial variation. Okay, so that completes our discussion on coordinate systems. Now we shall properly start discussing electrostatics. Okay, I'll start the new presentation. Please bear with me. Today, we have a few important things to discuss. Today, we also have a tutorial. So today is the 5th tutorial day. Of course, whatever is covered in today's tutorial will be a part of your examination. And also, let's see how far we can cover in the theory class today. So first, let us begin the discussion on basic ideas of Coulomb's law, which is an experimental law. We will be talking about electrostatics. This is our proper physics discussion is beginning now, right? So we have finished all the mathematical necessities, preliminaries. Now we will begin the discussion of electrostatics. This is the start of proper electromagnetic theory. Okay, right, let's see. So this is, the subject of electrostatics is about charges, electric field arising due to charges that are at rest. Source charges. Source charges meaning charges that are the source of electric field, the electric field. And we look at an experimental law known, familiar to you as Coulomb's law. What does it say? Coulomb's law says that suppose you have a source charge, small q, at a position r prime, vector. Okay. And you have a test charge, capital Q, at a position, capital R. then the displacement between small q and capital Q is vector r. I mean, this small r. Okay. This is the source charge, this is the test charge. What do I mean by test charge and a source charge? A source charge is one that gives rise to the electric field. I'm not making any restriction as of now on whether it's a positive or negative charge. It could be either of the two. And what is a test charge supposed to do? A test charge is supposed to test the presence or the strength of that electric field, right? So that is why. Unless only a charge can feel an electric field, nothing else will be able to feel an electric field. That point, I mean, for instance, a charge neutral matter will not be able to feel electric field, right? So to test whether the electric field has arisen due to the source charge or not, you need a test charge, right? And the force on the test charge due to the electric field that has come about because of the source charge is given by this formula. What is it? It is proportional, the force of interaction. I've written a few things. We'll discuss this thing in detail a little. The force of interaction is small q into capital Q by r squared. Small q, so force of interaction is proportional to the value of the source charge, is proportional to the value of the test charge, capital Q, that is to say jointly proportional to both the charges. Magnitude is inverse square of the scalar magnitude of the displacement between the two charges, the separation between the two charges. And then there's this unit vector r cap. What does it say? That the direction, force means a vector, it has a direction. And so the direction depends, I mean, the direction is only along the straightest path from small q to capital Q. That is, it's not going this way or that way, twisting or turning like a sine wave or whatever. So it is just a straight line. That is the direction along which the force will act. Okay, and then there is a constant of proportionality. This is nothing universal. This all depends on the system of unit that you have chosen. In the SI system of unit, MKS, which is defined from mechanics, meter, kilogram, second. In that system of unit, you will have the constant of proportionality to be this, 1 by 4 pi epsilon naught, where epsilon naught is known as the permittivity of free space, and its value in the SI system is 8.85 into 10 raised to minus 12 SI value, which is farad per meter. I hope you are aware of that fact. Okay, and as I said, small vector r is the difference between the two position vectors, capital R and capital R prime. Before I move on, I'd like to stress an important point. Typically, it happens, it is desirable that the source charge should be large. It should produce a very strong field because you need to test the field. So the stronger the field, the easier will it be for you to test it. And the test charge will have a charge, but as small as possible, like infinitesimally small possible. Why is infinitesimally small? Because if it were to have a significant charge of its own, then it will create its own vector field, electric field, and disturb the original electric field. So that is the reason why a test charge, just for the purpose of testing, should have only as small a possible amount of charge, small an amount of charge as possible, but not more than that. Just enough charge to test the field. Like, you know, gravitationally speaking, the Earth is a very large object. It has got a mass of 6 into 10 raised to 24 kg. It creates a strong gravitational field. And you have a mass of something like 70 kg, 60, 70 kg or whatever. So you can be a small test object to feel the gravitational field of the Earth. And indeed, you do feel the Earth's gravity. So that is what it is like. Okay. So one last point to stress, that Coulomb's law is an experimental law. This is a physical input. Nobody has derived this law mathematically. It's a first principle of nature. We are doing physics here. Physics means the study of nature, and the first principles of physics must always come from nature. So it's not something that has been derived by a mathematician. It is just expressed in the language of mathematics, but this phenomenon is an experimental fact that nature tells us. We shall look at another experimental observation, experimental law, known as the principle of superposition. Okay. experimentally observed thing. This is also a very important law. Let us see. Here, you have got a whole bunch of source charges, all with small q's. Remember the convention that we have adopted over here, the symbol convention that we have adopted here, is that the test charge, sorry, so the source charges come with the small alphabet and the test charge comes with the large alphabet, the capital alphabet. Okay, so you've got a whole bunch of charges, Q1, Q2, Q3, Q4, like that, scattered randomly in space. Each charge has got a position R1 prime, R2 prime, R3 prime, R4 prime, etc. And there's a test charge. This test charge is feeling the electric field of all the individual source charges. This test charge, a single test charge, is being used to test the electric field of all the source charges. And the position of the test charge is at the position vector capital R. Okay, so what is the total electric force experienced by this test charge? Let us see. This is a very important statement. The electric field force experienced by the test charge is the individual electric field, F1, let us say. What is F1? F1 is the force arising due to the source charge, electric field force that the test charge experiences due to the source charge Q1. F2 is the electric force due to the source charge Q2. And likewise for F3, F4, you can have n number of charges, no problems over there. So what is the most important thing is that this test charge Q, capital Q, experiences a force that is just the sum of the individual fields and nothing more. What do I mean by that? Meaning that you don't have to worry about how this charge Q1 and Q2 are interacting between themselves, or Q1 and Q3, or Q2 and Q4. These charges may also be interacting among themselves. But as far as this source charge is, the test charge is concerned, the interaction among other source charges is not a matter of concern. That is how it is. Like, you know, in foreign relations, India and Pakistan, they have a certain interaction, not a very friendly interaction. India and Russia as a country, they have a very friendly interaction. India and America, somewhat friendly interaction. But then America also interacts with Pakistan, and Russia also interacts with America, Russia also interacts with Pakistan. So the Indian Foreign Ministry says that how these countries interact among themselves is not a matter of our concern. What matters is how we stand with respect to each of these countries. So your two friends, for instance, India and Russia are friends, India and America are also friendly, but America and Russia are not very friendly. But however, that doesn't affect the relationship between India and Russia or India and America. So it is like these things. These are like the other countries. This capital Q is like our country. And what matters is this individual interaction. So we will not get any effect of how these two charges are interacting among themselves, etc., on this test charge. So that is how it is. So that's interaction between any two charges is not influenced by the other charges. Here, when I say any two charges, I'm talking about Q1 and capital Q, Q2 and capital Q, like that. So our test charge here will only have individual interaction with the other charges, and the total field force experienced by our test charge will not depend on how the other charges are interacting among themselves. This is known as the principle of superposition, linearly superposed. It's a very important law, and also this is an experimentally observed law. There is no reason why it should, I mean, there is no mathematical derivation of it. You just have to make measurements and come to this conclusion in the laboratory. So now let us see what is the individual force of interaction on each of the on the test charge due to each of these source charges. So if a source charge has got the label I, as in 1, 2, 3, 4 here, 1, 2, 3, 4, all these things here, then the force of interaction between any source charge and the test charge capital Q will be Q subscript I into capital Q divided by Ri squared here. R1, R2, R3, R4, this scalar distance squared into the unit vector along the straightest path between a source charge and the test charge. So that's the unit vector, radial. So if you are on this track R2, then the unit vector will be R2 cap. So like that. Or if you're on this radial vector R4, the unit vector will be R4 cap along this straight path. Either this way or that way, that entirely depends on the sign of charges. I have drawn the arrows going towards the test charge, which means that these arrows are coming from the source charges. Immediately, the direction of arrows implies that the source charges are positive. Remember this one thing, positive charges throw field lines out. Negative charges draw field lines towards themselves. Okay. As a source, that is. Okay, what about these radial displacements? Vector Ri, capital R minus position capital R minus position capital R subscript I. That is what it is. And unit vector will be vector divided by its magnitude. So this is another physical point of information that you have to know by making measurements in the laboratory. Okay, so with these 2 points of information, let us now build up our mathematical theory. Let us see how it is. Fi. Fi is the force due to an individual source charge, Fi. Okay. And that is Q into, now let us be a little careful, electric field EI. What is electric field? If you look at this formula, except for capital Q, everything else, all the other variables, of course, 1 by 4 pi epsilon naught is a constant quantity, except for capital Q, all the others are depend on the source charges here. So you can take capital Q outside, and then just look at this thing as Qi, small qi by Ri square into Ri cap into 1 by 4 pi epsilon naught as an individual package. What is that individual package called? That individual package is called the electric field. 1 by 4 pi epsilon naught, small qi, Ri squared, Ri cap. So this electric field, what is EI? EI is the electric field due to an individual source charge. Like that, it happens. Okay. What is the total electric field? Now, if you look at this formula, you should be able to figure out immediately. If you look at this formula, for every term in F, F1, F2, F3, Fn, whatever you have, every term in F, Q is a common factor. Q is going with every Fi. Every Fi has capital Q. So I can take the Q as a common factor out of this thing, and then I'd be left with a sum of the individual electric fields. So that is that sum. This whole thing EI summed over from 1 to n multiplied by Q will give you the field force, total force F. Capital F is equal to Q into E. And what is E? This electric field E? E is equal to summation of the electric field due to all the source charges. I is equal to 1 to n. Now, okay, so I can now write this total electric field in terms of the summation, and the summation will go over all the i's. 1 by 4 pi epsilon naught is a constant quantity. It comes out of this. So here in this formula, I'm applying this thing. EI is written like this. And then 1 by 4 pi epsilon naught is a common factor. It comes out of the summation. And then basically you just have to make a discrete summation of Qi by Ri squared, Ri dot over here. Okay, so I'm sorry, I made a mistake. It should be I dot here. Okay, so that's a discrete summation. Oh, that then what we have is, suppose instead of having discrete distribution of charges, point-like charges scattered all in space, instead of that, suppose I had smeared out the charges in a continuum jelly-like thing, like the way you apply butter to bread, or some, something that you can spread out, like a jelly or jam, whatever. So instead of having discrete dots, like, grains of sugar, or grains of rice, you have butter or jelly uniformly spread out. Then what will happen to your discrete summation? Let us see. As soon as you have a continuum distribution, the discrete summation goes to an integral. You can see that this thing and this thing are the same, except that this is when you have the charges distributed scattered in space like dots, point-like objects, and this when the charges are spread like the way you spread butter on bread. So that is what you have. So in that case, the summation, you take a small element of charge dq in space, sum over all space, that dq by r squared, you sum over all space r cap. That's the continuous distribution of charges. Now, some few things to talk about. Although if you are an astute observer, you'd be able to immediately ask me a difficult question. But I shall not get into that question right now. What about dq? dq, suppose I have given a straight line full of charges, a copper wire. A copper wire has got free charges. So unit length of that copper wire has got lambda amount of charges. Lambda is the charge per unit length. That's the line charge density, charges per unit length. So in a small element of line dl, the amount of charge contained will be lambda, line charge density, into dl. That will be your dq. Okay. Suppose instead of a copper wire, I have given you a copper sheet. If it's a copper sheet, then the charges will be distributed all through the sheet like a plane, right? Then what is the total amount of charge contained in a small area element dA? That will be surface charge density, charge contained per unit area into a small area element dA. That's the surface charge distribution you have. And a volume charge distribution, this is the easiest actually. Why? You have been given a small volume element d tau. I hope you can now see why I have spent so much time discussing line element, area element, surface element, all those things. DL is line element, dA is area element, d tau is volume element. You have worked on all these things. Just a while ago, we discussed the volume element of a sphere, r squared, dr, sine theta, d theta, d phi. So that, in that small volume element d tau, the total amount of charge contained, which is dq, is equal to charge density, volume charge density, charge contained in charge contained in unit volume, multiplied by the volume itself, a given volume, d tau, rho d tau, sigma dA. Lambda is charge per line. So in the Coulomb SI system of unit, its unit will be Coulomb per meter. This will be Coulomb per square meter, sigma, surface charge density. And rho, this will be Coulomb per cubic meter. And total amount of charge contained will be Coulomb per meter into a small line element. This is Coulomb per square meter into a small area element. The area and the sigma will cancel. And similarly, this will be Coulomb per cubic meter into a small volume element, which is also cubic meter in the SI system. And so you'll have a cancellation. So that's the continuous charge distribution that you have. Now, I said that there's a little bit of conceptual difficulty over here. Volume element doesn't have that difficulty because volume element is a scalar quantity. Density over here is also a scalar quantity. Charge is also a scalar quantity. So rho into d tau, you get a scalar. Charge is always a scalar quantity. So now I'm writing lambda, which is a scalar, multiplied by dl. dl is actually a vector. dA is actually a vector. But I have not concerned myself with the vector part of it. I've just taken the magnitude part of that vector. So this is just the magnitude of the line element. This is the magnitude of the area element. Magnitude times the density, magnitude, surface area density. This is line element magnitude times the line charge density. So that is the one important point you should. So this is a vector. In reality, line element is a vector, surface element is a vector, but volume element is a scalar. So with these two vectors, you have to be careful. You have to just take the magnitude part of it. Anyway, now that we have finished this discussion, we shall go to finding out electric flux. And you have already worked on the Gauss divergence theorem, where we have talked a lot about fluxes. So we shall see now what happens with flux here. Let's see. Flux of the electric field. What is flux? I said earlier, it is to be imagined or understood, not to be defined, as the total number of field lines passing through a given area. Right, but you know very well that these field lines are in a continuum distribution. There will be infinite number of field lines. So small area, large area, it doesn't matter. It will be an infinite number of field lines. So that's why I said it's not really a definition. It is to be conceptualized or understood. I mean, infinity through a small area and infinity through a large area are the same thing. Infinity is infinity, whether small area infinity or large area infinity. This sort of distinction doesn't matter. Anyway, so suppose you have a bunch of electric charges, right? Or let's just say some charge, one charge, a single charge, an isolated charge, and its electric field E is equal to 1 by 4 pi epsilon naught Q by R squared R cap. Okay. Now this electric field is placed somewhere, let us say origin of coordinates. Okay. This electric field is enveloped by a surface. Enveloped by a surface, let us say a spherical surface, but it doesn't have to be a spherical surface, and I'll tell you why. But for convenience, you think that you have a charge placed at the origin of coordinates, x, y, z axes. So it is there at the center of coordinates, O, and you have enveloped the charge all around with a closed bubble, spherical bubble, whose origin, the spherical bubble has got a radius, and the center of the spherical bubble is also at the origin of coordinates. So the position of the charge at the origin of coordinates and the center of the radial spherical bubble are both coinciding at the origin of coordinates. Fine. Okay, what is the total flux due to this electric field? What is the total flux? Number of field lines crossing that spherical surface with which you have enclosed the charge at the center. And here comes our important thing. I told you in spherical problems, the outer surface will be very important. Area element of the outer face, dA, is equal to r squared sine theta d theta d phi r cap. That's spherical symmetry. dA r squared sine theta d theta d phi r cap. Okay, so what is the flux then? dA is this thing. It has got an r cap. Electric field has also got, here, an r cap. So when I take the dot product of this and this, E dot dA, what you will have is, I'm sorry, I made a mistake. I mean, it's not really, kind of casual writing. This dot shouldn't be there. Although we casually write dot as the thing for products, but here when we are writing dots, we have to be careful. This dot is of no account. This dot matters because when I say dot, when we are dealing with vectors, you have to be very careful about where you're putting the dot. I also put a dot over here. But ignore this dot and this dot. They are just kind of a confusing thing, presence. So let us see now. You have Q by 4 pi epsilon naught r squared, just the scalar part of it. Then you have this r squared sine theta d theta d phi, just the scalar part of it, r squared sine theta d theta d phi. Then you have an r cap from here and an r cap from here. That dotted, those two are dotted with each other, and they will give you 1. We have discussed this thing earlier also. All unit vectors dotted with themselves will give you 1. Unit vectors have only magnitude of 1. R cap dot R cap. Here you have 1. Okay, but something much more important is happening over here. You have an r squared here in dA, and you have a 1 upon r squared in E. Those two are going to cancel each other. Those two will cancel each other. R squared here and R squared here. And what are you left with? Q is a constant quantity. It comes out. Q by 4 pi epsilon naught is the flux. Q by 4 pi epsilon naught comes out constant. Then you're left with sine theta d theta, and you're left with d phi. Not to lose sight of the fact, not to lose sight of what I told you about the limits of the integral. Theta will go from 0 to pi. Phi will go from 0 to 2 pi. Okay. Compute the integral. There's a whole lot of things to be discussed here. Flux capital Phi, by the way, sorry, there's just something else I should also stress upon. This is also Phi, and this is also Phi, except that just like you can write A in two ways, this is small a, and capital A can be written as, capital A the way you write it. So similarly, this is small phi, and this is capital Phi. Total flux, capital Phi, like that, and this is small phi. So the total flux is equal to E dot dA, integrated over all surface. When you have a surface integral, there will be two integrals. You cannot avoid that. When you have a volume integral, there will be three integrals, like that. So when you integrate this thing, when you integrate sine theta, you will get minus cos theta. Minus cos theta going from 0 to pi. And phi integral will give you 0 to 2 pi. So you'll get 2 pi here, coming from the phi integral. Q by 4 pi epsilon naught is already there. Okay, now let us worry about the cosine part of it. The minus sign comes out. Cos of pi is minus 1. Minus of cos of 0. Cos of 0 is 1. So minus 1 is minus 2. Minus 2 into minus outside will be plus 2. Plus 2 into 2 pi will be 4 pi. 4 pi by 4 pi will cancel out, and you're just left with Q by epsilon naught. Now, I'd return to this discussion. You can very well ask me, now why have you enclosed it with a spherical surface? Why not any other surface? I'm giving you a short answer. If you enclose it with any other surface, the final answer will not be different. It will still be Q by epsilon naught. You can check it with any other surface configuration you can want, but it has to be a closed surface, of course. You can close it within a cylinder and convert all the unit vectors of a cylinder. This thing will have an R, whereas you can other enclosing surfaces will have other kind of dependence on its own coordinate system. If you uniformize all the coordinates and do all your calculations, complicated calculations, everything, you'll still come to the same thing. What is the most important thing over here? Why do you think that is happening? It is happening because of this 1 upon r squared and this r squared cancelling. You notice this thing? The final result does not depend on the geometry of the surface that you have chosen. That's another way of answering this question. The final result, Q by epsilon naught, what does it depend on? Just the value of the charge, nothing else, and of course the electric constant, epsilon naught. If it had contained information on the geometry of the surface with which you have enclosed the charge, then the geometry of the surface with which you enclose the charge would have been important. But the final result will always be free of the geometry. Let me just go to the next page. This diagram will make this point clear. For the time being, ignore all the other things over here. I've written multiple charges, but this diagram should suffice to explain my point. Ignore all these arrows and everything. I have got a Q1 and Q2, ignore all that. Let us just say I've got a single charge Q. Just single charge Q, which I've placed at the O, center of the sphere O. This single charge Q will be throwing field lines uniformly in all directions, and everywhere on the surface field line density will be the same. The same number of field lines will cross this spherical surface everywhere. the number density of field lines per unit area will be the same. Suppose, what is flux? Flux will be the total number of field lines crossing this surface area. Okay, fine. But suppose you say that, okay, what I want to do is that I will press this sphere and throw it completely out of shape. You press, twist, and turn, and this nice round sphere becomes like a potato, badly misshapen potato or whatever. Then what will happen? The number of field lines, you follow this point carefully, the number of field lines crossing that misshapen surface, that distorted surface, will still be the same, except that at some points the field lines will become more dense, at some other points the field lines will become more sparse, spread out. So from point to point on a badly distorted surface, the surface density of field lines will change, but the total number of field lines crossing that surface will still be the same. You can have a sphere, surface density will be uniform, total number of field lines will be a given quantity. You distort this sphere into something else, the surface density of the field lines will change, but the total number of field lines will not change. And that is what is important to us. We are concerning ourselves with the total flux. What is the total flux? The total number of field lines crossing the enclosing surface. Regardless of the shape of the surface, the total flux will not change. And indeed, it doesn't. It just depends on the number of charge, amount of charge enclosed within that surface. It does not depend on the geometry of the surface. So Q by epsilon naught is what you have. Now suppose we have done it, what we have done is with an individual charge. Suppose we do it with a bunch of charges. Now let us come to this discussion as written over here. Suppose we come to a bunch of charges and they're all scattered within an enclosing volume. Once again, I stress the enclosing volume can have any shape, but for convenience of understanding, I have drawn a spherical, or given the impression of a spherical surface. This thing is helpful. If I draw a spherical surface, immediately I'd be able to write the outer surface area element. That's the point. Otherwise, it doesn't matter. It could have chosen any other kind of surface. Okay. So each of these individual charges will throw out its electric field Q1, Q2. I've just drawn two, but there can be many other charges also. And I've just deliberately drawn like they have a symmetric position, but they need not have a symmetric position. What do I mean by that? I'll come to that point briefly. Okay. So what is the total flux? Capital Phi is equal to E dot dA, where E is the total electric field due to all the charges within that enclosing spherical volume, E dot dA. And what is E? E is equal to E1 plus E2 plus E3, etc. So we put this summation EI here, and then I'm writing surface integral of EI dot dA, E1 dot dA, E2 dot dA. These are all surface integrals, E3 dot dA, and then all the way up to En dot dA. In so doing, I'm applying the superposition principle. I hope you are aware of what I'm driving at. What is the superposition principle? Just a while ago, I discussed the superposition principle here. All the electric fields will be, this will be capital Q into E1, this will be capital Q into E2, this will be capital Q into E3, and this last one will be capital Q into En, right? So that is what it is. And then with every E, I'm carrying out a surface integral. Here we are. So all of these things. Next thing, this is integral of the summation of the electric fields, integral of the summation of the electric field. Now, after having written like this, it's become the other way around. Earlier, E contained the summation. So the summation EI first, then the integral later. This E is this thing, sigma EI, summation EI. So you can see from these two formula that sigma comes first, then the surface integral later. But as soon as you have decomposed it and written it like that, then immediately the two integral and the summation have changed places. So now that's what happens because of superposition. Okay, so Now, earlier we had integral of the summation. Now we have summation of the surface integral, closed surface integral. And what is the closed surface integral? E dot dA, EI dot dA. And what is EI dot dA? If you have an E dot dA will give you Q by epsilon naught. E dot dA over a closed surface, as has been written over here, gives you the flux to be Q by epsilon naught. And here we have to do just that. EI dot dA summation Qi by epsilon naught, Q total by epsilon. Summation, all the charges contained inside will contribute to the total flux. A whole lot of discussions have to be held now. First, let us see. I've written something over here. All charges appear to be at the center. Now let us try to understand. First, I've written a whole lot of things over here. We shall go through all of them and understand the meaning of what I have written. All charges appear to be at the center. Deliberately, just for convenience of understanding, I have drawn these two charges, Q1 and Q2, like they are from at the same distance from this axis. This is the origin of coordinates. From here, you have drawn an outward going vector. Let us say an observer is standing over here and measuring the field strength, or a test charge has been put over there, and the test charge is measuring the field strength of all the individual source charges enclosed within this volume, or enclosed within this surface, spherical surface. Okay, so here you have a charge Q1, here you have a charge Q2. Q1 is throwing field lines in every direction. Q2 is also throwing field lines in every direction. The field lines are penetrating the enclosing surface. That contributes to the flux, as you can see. So this is the flux, this field line, they're all coming out of the surface. So they will be contributing to the flux through that surface. Okay. So here you have a test charge. This test charge will experience the field line of Q2 coming from this side and Q1 coming from this side. Now you follow the discussion carefully. The two charges are actually here and here. This test charge is here. Now this field line coming from here can be decomposed into two components. One is this component and the other, the vertical component, so to speak, and the other is the horizontal component. This field line has been decomposed into two components. Similarly, this field line going to this side is decomposed into a vertical component and a horizontal component. And the two horizontal components, you can immediately see, being opposite of each other, will cancel out. And what will happen is that the vertical component will get reinforced. If the vertical component is reinforced and the horizontal components get cancelled, then as far as this test charge is concerned, this test charge is experiencing an electric field due to a hypothetical source charge that appears to be at the center. It's as if these two charges are here at the center now, and from there it is throwing out a field line, and this test charge, a test charge here, will experience that field line. Although I have drawn a highly symmetric diagram, which you can say looks like a particular case, but in actual fact, if you have other charges, you can extend the argument to other charges randomly distributed throughout all space, and this principle will hold. All charges appear to be at the center. This is the same principle that applies for gravity also. I believe you are aware of the fact that in the case of gravity, suppose this is the surface of the Earth, a spherical surface. You are standing somewhere on the surface of the Earth. Fine, very good. You read, although there is earth matter directly just under your feet. You are standing on the earth matter. But the gravitational field that you will be experiencing could very well be due to, if all the earth matter beneath your feet were to have collapsed at the center, if you were somehow held to the position where you were earlier. Of course, if the earth starts collapsing under your feet, you'll also be heading towards the center of the earth. But somehow, let us say you manage to remain suspended in space, although the earth matter under your feet collapsed at the center. Wouldn't have mattered in the least. You would have still experienced the same gravitational field. That's why in the case of the earth, it's the same principle that applies, as if that the gravitational field that you experience standing on the surface of the earth could very well have been due to all the earth matter packed like a point at the center. That is what it is. Why am I talking about gravity? Simple answer. Whatever we have discussed for Coulomb force here will also apply to gravitational force because of one great similarity between gravity and electrostatics, namely 1 upon r squared. This r squared and this r squared for a spherically symmetric surface element would have cancelled, and there you would have had the same thing. Okay. Now comes, so I have explained, I hope, this point. All charges appear to be at the center. This is the superposition principle that I explained a while ago. It comes from F1 plus F2 plus F3 plus Fn plus all the way up to Fn. That is what it is. Now comes something important here. Let us see. So it is like the total flux due to a bunch of multiple charges, enclosed within a closed surface would be just the summation of all the charges divided by epsilon naught. It will be equal to the total charge enclosed within a closed surface. Q total is equal to the Q enclosed, closed surface. Very important point, I've drawn a star here and then I've written something here with reference to that star. Flux lines cross the closed surface an odd number of times. Electric field lines diverge. They don't curl. Recall our discussion of divergence and curl. Electric field lines diverge. They don't curl. Meaning, let's say you have positive charges, right? And so field lines due to positive charges will start and keep diverging all the way out to infinity. They will never come back. So such a field line will cross this spherical surface only once on its way out, and it will not come back. So basically, it would have crossed this spherical surface only once. So flux lines cross the closed surface an odd number of times. If you'd had a misshapen surface, what matters is not the geometry of the surface, but the position of the charge with respect to the surface. Now, what do I mean by that? Let us try to understand. I have gathered all the charges within this enclosing surface. And if it is within the enclosing surface, then the field lines due to an individual charge will cross the enclosing surface only once. This is a very simple surface, a sphere, only once. Now, suppose you will say, okay, fine. I mean, so what is the, I've written charge enclosed within a closed volume. This within is very important. It's written in capital with an underline, highly stressed, very important point. What if I had a charge outside? Just try to imagine. I have a charge not within this surface, but outside. Here I have a charge. What will this charge do? It will throw a field line which will pierce this surface and go inside. Follow this point carefully, please. It will pierce this surface, go inside. But then it will keep moving on and then pierce this surface and go outside. It has crossed the surface an even number of times. Entered once, exited once. Therefore, its contribution to the flux is zero. Why? What is going in will be cancelled by what is going out. That is the important point. So if you have an even number of crossing of a surface, then that field line does not contribute to the flux. If you only have an odd number of crossing of a surface, you will have a net contribution to the flux. And so here you have a charge within this surface, and it crosses the surface only once. It can cross 3 times also. Suppose instead of a spherical surface, you have a charge like, let us say, a kidney, a surface that is shaped like a kidney. I hope you know what a kidney is shaped like, or maybe even a rajma dal. You know what a rajma dal is shaped like. It's a little curved, right? So you have a charge placed in one corner of that curve. It will cross one branch of that bean outside, then go into another branch of that bean inside, and then again cross outside. Net number of crossing, 3 times. Or you can even think of a donut. A donut is kind of a, a ring-like thing with a thick I don't know what you call it, whatever. Annulus. Yes, it's a very thick annulus. Inside a donut, a field line will cross the annulus once, then it will go through the empty center to the other branch, cross the annulus inside again, and then go outside. It would have crossed 3 times. So any charge which is enclosed within a surface will contribute to the flux. If it is a charge that is outside a surface, will not contribute to the flux. That is the point I made. Flux lines cross the closed surface an odd number of times. So that is the point that has been made over here. Now comes something very important. This is known as the integral form of Gauss's law, not theorem. You have studied the Gauss divergence theorem, but here we are not talking about the Gauss. I mean, we are talking about Gauss's law of electrostatics. What does it say? This is the integral form. It involves an integration, closed surface integral E dot dA phi. This integral is equal to charge enclosed, total charge enclosed within the volume by epsilon naught. You can apply the same principle for gravitation. For gravitational potential, instead of Q1, 1 by 4 pi epsilon naught into Qi by Ri squared, etc., all that, you have this thing. So, I mean, I've made some mistakes over here. First of all, I should not have written an E here. I should have written an F here. And it should have written an I here and I here, whatever. But that doesn't matter. R squared and R cap are the same in both the cases. You have 1 by 4 pi epsilon naught here replaced by minus G. So, if in your flux you have just 1 upon epsilon naught, then 1 upon epsilon naught will be replaced by minus 4 pi G. Just do it. It's not really necessary from the point of view of our syllabus. So, this is gravity, but you just have minus 4 pi G. Okay, so you have minus 4 pi G here, and here you have got epsilon naught, 1 upon epsilon naught is replaced by minus 4 pi G. Okay, and so then you have got charge replaced by summation over charge is replaced by summation over mass. Mass enclosed minus 4 pi G into mass enclosed. Okay, so that is what you have. Now comes something important. We have studied Gauss's law of electrostatics. I mean, you may ignore this gravitational potential part. It's not really needed from the point of view of our syllabus. So you can ignore that part, gravitational potential part. This is what you have. So integral form of Gauss's law of electrostatics. This is what it is. E dot dA is equal to charge enclosed by epsilon naught. Okay, that is the integral form. But then there is also the Gauss divergence theorem with which you are familiar, the Gauss divergence theorem. And what does it say? Divergence of a vector field, volume integral of that will be equal to the closed surface flux of that same vector field. So this and this make the Gauss divergence theorem. This and this make the integral form of Gauss's law of electrostatics. Be clear on that point. Integral form of Gauss's law of electrostatics. Okay. Now, let us see what we can do with this charge enclosed. Charge enclosed, follow this. This is just algebra, no physics any longer. We have got the physics enough. Charge enclosed is equal to rho d tau. You have also worked on some tutorial problems involving all this business. Rho d tau, dq is equal to rho d tau. Okay, so there you have. I have written this thing, rho d tau with the volume integral. I'm sorry, over a volume. This is a volume integral. Volume charge density is rho. Now, follow this point carefully. Rho divergence of E d tau volume integral is equal to charge enclosed by epsilon naught. This is equal to this. This is equal to this. Therefore, this is equal to this. Charge enclosed by epsilon naught. Okay, what we will do is we will write divergence of E d tau volume integral is equal to charge enclosed by epsilon naught, and instead of charge enclosed, I'm writing rho d tau volume integral. Epsilon naught is a constant quantity. It goes inside the volume integral, rho by epsilon naught d tau. Okay. Now you make a comparison between the left-hand side and the right-hand side. The left-hand side has got divergence of E. The right-hand side has got rho by epsilon naught. The left-hand side has a volume integral. The right-hand side has a volume integral, d tau and d tau. Next thing is for you to say divergence of E is equal to rho by epsilon naught. This is a local description. Differential form of Gauss's law. A whole lot of things will have to be discussed now. First, this point. Flux is equal to closed surface integral of the electric field. Electric field is equal to total charge enclosed by epsilon naught. So charge enclosed charge enclosed within a closed surface. So that is the integral form of Gauss's law. This is the differential form of Gauss's law, a local description. What do I mean by the word local description? I think we have discussed this thing earlier also. I told you in the context of local and global description using differential equations. Differential equations, what are differential equations? Differential equations are equations that contain a derivative. What is the use of a derivative? A derivative is one that captures something, is a mathematical operator, a mathematical something that captures rate of change locally. A derivative of a function tells you what is the rate of that change of that function, or how that function is changing from one point of space to another. That is the property of a derivative. Whenever you have an equation involving a derivative, you have a differential equation. A differential equation is one that captures changes locally as a function is changing. That is why we have written divergence of E is equal to rho by epsilon naught is a local description. You just go back to the integral form of Gauss's law. Let us discuss this point. E dot dA is an integration. Integration over the entire surface. Global, not local. Over the entire surface of the Earth, find out what is the gravitational flux. And you'll say it's the total amount of matter contained into, well, minus 4 pi g. Epsilon naught. Remember, 1 by 4 pi epsilon naught g is equivalent, 1 by 4 pi epsilon naught in electrostatics is the equivalent of minus g in gravity. So 1 by 4 pi epsilon naught translates to minus g in gravity. So here, if you just have 1 by 4 epsilon naught, then the 4 pi must go with minus g. So that's why I've written minus 4 pi g. You can do it formally, it'll be the same thing. You can work on this thing and get the same answer. But this is a global description, total amount. What do I mean by global description? You are referring to the total amount of charge contained in the entire volume. In this entire volume, what is the total amount of charge? All over the world, globally, all over the world, all over the globe, globally, you have captured the total amount of charge contained. But this equation is not referring to the total amount of charge contained. It is referring to a local quantity called density. At this point in space, what is the density of charges? Both, if you look at this equation, on the left-hand side, you have electric field. On the right-hand side, you have charge. However, the packaging is different. In the differential form of Gauss's law, you have derivative of the electric field, derivative as in the divergence operator, and on the right-hand side, you have the local charge density. Here, on the left-hand side, you do not have the derivative of the electric field, you have the integral of the electric field over the entire surface. And on the right-hand side, you do not have charge density, you have total charge contained in the volume. Just think of it. I ask you to find the density of the Earth's atmosphere. Earth's atmosphere. What will you do? Will you go running all over the surface of the Earth to find the density of the Earth's atmosphere? Not needed, really. It's a symmetric distribution. And I mean, everywhere on the surface of the Earth at sea level, the air has the same density at sea level. Be careful about that. If you go to the top of Mount Everest, the density will change. But at sea level, the air density will be the same. So you don't have to. If I ask you to find the density of the Earth, I mean, how do you find density? You'll have to take the total amount of substance, then divide by the total volume. But you don't have to worry about doing that. You can just find what is the density of the Earth's atmosphere in your own room, in your own cubicle, in a little bit of closed container that encloses the entire Earth. I'm sorry, in entire, I mean, that encloses air. So a little bit of air in your room, you can find out how much I mean, it's not, incidentally, it's not very easy to find what is the mass of air contained in your room. I wonder whether you are aware of things called kinetic theory or thermodynamics. That's the way you should be able to find what is the total amount of air contained in your room. You can, but you can find the amount of air that is contained in your room. Measuring the volume of your room is a very simple exercise. You just have to put a scale all along the ground, length and breadth, multiply the area. Then you have to put a scale along the height. Area into height will give you the volume of the room. So you get the volume of your room, and then you divide the amount of air contained in your room by the volume, and you'll be able to tell me what is the air density just by. That is the point I'm trying to make. This is the point I'm trying to make. Be careful in understanding that. If I ask you to find the density of the Earth's atmosphere at the sea level, you don't have to run all over the Earth. Just measuring the density of the Earth's atmosphere in your room locally, just be located where you are. Just the local information will give you the correct answer. But if I ask you what is the total amount of total mass of the Earth's atmosphere, then you can't just sit in your room. Then you'll have to travel all over the Earth and find out the air enclosed or air trapped by gravity. Air is not enclosed within any closed surface, but air is trapped by the Earth's gravity. Incidentally, in the case of the moon, the gravity of the moon is far weaker than that of the Earth, and the moon is hotter. And if the moon is hotter, then the particles in the moon's atmosphere, when it had an atmosphere, travel faster. Hotness means particles are traveling faster on an average. And if they travel faster with a weaker gravity, they were weak with the weak gravity of the moon. The atmospheric particles of the moon were able to escape the gravity of the moon, escape velocity. They attained escape velocity. So it is that with the case of the Earth, the gravity is stronger and the Earth is cooler. If the Earth were to become very hot, extremely hot, not just very hot, extremely hot, in which we wouldn't be able to live, then you will have all the particles of the Earth's atmosphere escaping the Earth's gravity. Anyway, so you will have to travel all over the surface of the Earth to find what is the total amount of atmosphere contained. So whenever you go all over the Earth and find the total amount, you are doing an integration. That is a global description. Whenever you are trapped at a point whenever you can remain at a point in space and make measurements such as density and all those things, you have a local description. This is known as the differential form of Gauss's law. Both forms hold for any arbitrarily shaped closed surface. This is very important. This point has to be understood. That a while ago I discussed that regardless of the geometry of the enclosing surface, it doesn't matter whatever be the kind of geometry. All that matters is how much charge is enclosed within that. The only difference between a symmetric surface and a non-symmetric distorted surface is that, as in the case of this symmetric surface, the field lines will cross this surface uniformly everywhere. The flux will be uniform everywhere. but the total flux will be just the same if the surface were to be distorted, except that in a distorted surface, the flux will not be uniform everywhere. At some points it will be more, at some points it will be less. The local flux density, area, number of field lines per unit area, but overall the total number of field lines will still be the same. So that is the idea. So as I said, both the forms of Gauss's law of electrostatic, differential form of Gauss's law, as well as the integral form of Gauss's law, both these two forms will have the same validity regardless of the geometry of the enclosing surface. Okay, and then this one last point is that divergence of E is equal to rho by epsilon naught is the first of the four Maxwell equations. I'll just briefly discuss this point. What are the Maxwell equations? We are going to work with two vector fields, namely the electric field and the magnetic field. The Maxwell equations are simply this. You take the electric field, take its divergence, find something. As in here, you've got rho by epsilon naught. Take the electric field, take its curl, find something. Since we are doing electrostatics, curl of E will be equal to 0 because E is just a function of R. It's a central field. And we have discussed this thing mathematically already. So curl of E for electrostatics will be equal to 0, vector 0. But Maxwell equations are going to work with electrodynamics. So we'll have to be a little careful. Anyway, what I mean to say is that Maxwell equations are simply taking the divergence and the curl of the electric field, taking the divergence and the curl of the magnetic field. So divergence of E is equal to something, rho by epsilon naught as you have over here, curl of E is equal to something. Divergence of B is equal to something, incidentally that something is 0. Divergence of B, magnetic field is B. Divergence of B is equal to 0, curl of B is equal to something. That package is just Maxwell equations. Two vector fields, E and B. On each vector field, you apply an operator, a vector differential operator. Namely, what? The divergence operator and the curl operator. That is the reason why we took so long to discuss divergence and curl, their specific physical implications, and how they might be worked on in different kinds of symmetries, coordinate systems, coordinates. So that is the reason why we spend so much time. Okay, now I shall have something very important to tell you. I hope all of you are listening carefully, please. This, whatever we have covered, all of you, I hope you're following, whatever we have covered up to this point, page 66 in the main set of notes, up to this point will be in your syllabus. There will be, so basically up to differential form of Gauss's law. That will be a part of your syllabus. You will get, that's up to where you will end. In the next class, we will discuss this thing in slightly, we will expand up whatever we have discussed up to this. We will expand slightly in the next class, and also in the next class, I shall also discuss some of the harder problems of the tutorials. Right, in the next class, we shall have a full discussion. That is on Friday. We shall have a full discussion on the examination pattern and strategy, everything. Just remember that up to page 66 is your syllabus. There will be a little bit added because of the supplementary notes, but the supplementary notes are just designed to add some extra points to this discussion. In the next class, we will discuss a few supplementary points. I have already discussed that in the class already today, but in the next class, I'll just touch upon them in greater detail, and I shall also discuss some harder tutorial problems. Today, you also have a tutorial in the afternoon at 2. This will be tutorial 5. This tutorial 5 will also be a part of your examination syllabus. So examination syllabus will be up to tutorial 5 and up to Gauss's law of electrostatics in both the integral form and the differential form. So I hope you are aware of that. I mean, you have understood this point clearly and correctly. So there should be no issues, I hope, after this. In understanding, so in the next class, we shall have a longer discussion on the exam pattern and all that thing.
Sir,
Yes,
sir, can you tell about the exam pattern?
no, not now, sir. I told you, we'll discuss this thing on Friday.
Okay, sir.
Sir, can you please upload this? Can you please upload this lecture notes?
So I will upload today's tutorial, the last 2 tutorials, all the lecture notes, everything within today or tomorrow, before Friday.
Okay, thank you, sir.
Okay, before Friday. Tomorrow I will have. Okay, anyway, I'm stopping the recording.